On this first spring day, right? All right, so Efthimios Kaxiras did his Bachelor of Science in Physics from the National Technical University of Athens in Greece, and then got his PhD from MIT, working with John Janopoulos, and then went on to do a postdoc at IBM Watson in Yorktown Heights, for which he received an IBM Research Division Award. And then I think, if I understand correctly, he went on to Naval Research Lab for a few years before he got an assistant professor position at Harvard, where he stayed ever since. He's currently the John Hasbrook von Vleck Professor of Pure and Applied Physics. Has chaired the physics department after chairing the applied math department. Was founding director of the Institute for Applied Computational Science at Harvard. So very distinguished fellow of the Institute of Physics of the American Physics Society. Broadly is a computational materials and condensed matter physicist. And sort of like, you know, I'm not sure if I characterize this correctly, but sort of takes a multi-scale approach in his work. So starting from first principle quantum mechanics all the way to microscopic scales. And so today, I guess we'll hear mostly, about Twistronics, which is of course a very fashionable topic in the study of 3D materials. And so without further ado, the floor is yours. Thank you very much.
Thank you for the kind introduction and for the invitation to come and give the colloquium here. As you said, it's a long drive from Boston. At least the day is beautiful today, so it's a pleasure. And it's a pleasure to be in campus here. Actually, a couple of my former students had strong interactions with other members of your department recently, Stephen Carr and Zoe Zhu. So through them, you may have heard some of the work that we have been doing in my group for the last few years. And this work has been focusing mostly on Twistronics, about graphene, but also a few other related two-dimensional materials. And the interesting thing is that we don't just have the layers themselves, but there's a relative twist between successive layers, which changes everything, as I will explain. And you'll see some versions of the multi-scale approach through this kind of discussion. So first of all, a little bit about sort of a bigger perspective, a larger perspective. Why are we interested in two-dimensional solids and materials? And there's a very long and rich history of these types of systems for generating very exciting physics, very rich physics in the two-dimensional electron gas. And I'm giving you here only a very quick review, a very short review of some highlights. And the field has become extremely important. So if you have electrons in a two-dimensional plane and you impose an external magnetic field, then they form these little circles, these orbits, which are known as Landau levels. They're quantized. The orbits that they form live on specific energy levels. Moreover, there's edge states which cannot form these orbits, so therefore they hop around along the edges of the sample, and the energy of the edge states does something very interesting. And if you observe the response of this system, for example, its resistivity as a function of increasing magnetic field on the horizontal axis, the classical behavior of electrons, the dashed line, is completely absent from a certain value of the field and beyond. And you see these staircase of values, and these values are very, very precise. One of the most precise types of measurements that we can have in physics. Those levels are at exactly fractions of the value of fundamental constants, h over e squared. So that's the quantized quantum Hall effect, and this is the resistance is in units of h over e squared. 1 over nu, when nu is an integer, that's the integer quantum Hall effect, but when nu is a fraction, as you see here several examples, that's the fractional quantum Hall effect. And the state of the system that produces this behavior was realized at that time to be a really new state of matter, because the quantization of these levels implies that the whole system behaves as if electrons had a fraction of their nominal physical charge. So this was very exciting, the quantized integer and fractional quantum Hall effects. So the quantum Hall effect was observed in 1980, and then related behavior, the quantum spin Hall effect, where electrons of different spins would circulate in opposite directions in the sample, was observed a few years later. And even the quantum anomalous Hall effect was proposed and then observed, in which case there's no external magnetic field, but the system generates an internal way of acting as if there's a magnetic field present, and this produced even more interesting behavior. So all this really brought a revolution in condensed matter physics on how we understand the behavior of a system of electrons constrained to be in 2 dimensions. And evidence for how exciting and novel these discoveries were is the number of Nobel Prizes that was awarded for these kinds of discoveries, starting with the quantum Hall effect, which was awarded to von Klinsing, and the fractional quantum Hall effect. Chewy, Stormer, and Loughlin, who did the theory, were awarded the Nobel Prize for this. My colleague at Harvard, Gerd Halperin, has discussed the edge effects, which are extremely important and very, very useful even for practical applications. And Haldane proposed the quantum anomalous Hall effect, and he also got a Nobel Prize for this. So really fundamental discoveries on how matter behaves under these conditions. But for a very long time, it was extremely difficult to produce the 2-dimensional electron gas using 3-dimensional crystals. So basically what people did after decades of refining the properties of these crystalline materials, they put two different materials together. This is aluminum gallium arsenide and gallium arsenide. And at the interface of these 2 different materials, you create a pocket here. The vertical axis is an energy scale. The horizontal axis cuts across the different materials. So there's an energy well there, a pocket where the electrons are localized. So these are the electronic wave functions in this pocket of the energy well. And this is what produces the 2-dimensional electron gas. And you can tell from all this that it was a huge challenge to actually make that happen. But after decades of very hard work, as I already mentioned, people were able to do this. In the last couple of decades, we have been really spoiled from that point of view, because nature has provided us, or rather we have discovered by carefully manipulating what's possible in nature, several 2-dimensional materials, truly 2-dimensional materials. So we don't have to worry about creating an interface between highly well prepared 3-dimensional crystals. And the prototypical material from this cornucopia of the materials is graphene, which is a semi-metal. But there's also different families of semiconductors and insulators, and some of those materials even become superconductors, and I'll discuss some aspects of this later in my talk. And the people who discovered graphene or created a single plane of carbon atoms graphene also got the Nobel Prize for this wonderful discovery, Andrei Geim and Kostya Novoselov. And now we have these materials to play with, and we can do all sorts of really exciting things. By the way, a freestanding graphene is not entirely flat by itself. It does have some corrugations, but typically it's encapsulated between other 2-dimensional materials, and that makes the whole system rigid and very, very flat. So the last less than 10 years, 5 to 7 years, so people have been perfected the way of creating these twisted layers. So they call that twist layer engineering. I guess this is from about 10 years ago from the group of Philip Kim. That's an experimental realization. of what happens when you put two layers of graphene on top of each other and you include a small relative twist between them. And what you see is this kind of super lattice, the Moiré length scale pattern, where in some regions the atoms on the two layers perfectly match each other, top and bottom, so you can only see one lattice. But in other regions, the two lattices are very much mismatched, and you see this very complicated pattern. So this introduces the Moiré length scale, which is much larger than the atomic length scale, and produces very interesting effects because electrons now have to obey not only the strict periodicity of the atomic lattice in each layer, which is there and unavoidable for the electrons, but they also have to obey the constraints imposed by this additional periodicity, the Moiré scale periodicity. And that's what produces all the exciting additional interesting effects. By the way, you should notice even from this picture a basic difference between a simple-minded Moiré pattern obtained by simply putting one layer on top of each other and what is actually seen experimentally, which is this very nice pattern of upward and downward pointing triangles, lighter and darker in shade in this scanning transmission electron microscopy experiment. I'll revisit that and explain the origin of this in the I think it's a crucial aspect of how the system behaves. So we now basically have an adjustable superlattice parameter to control the electronic behavior, essentially at will. And things became even more exciting in around 2018 when the group of Pablo Jarillo Herrero at MIT put such two layers of graphene with a slight twist between them and measured so this is the voltage across the sample as a function of the current. And for certain temperatures, below a certain temperature, there's no voltage drop. So basically, this is a superconductor. So the discovery of superconductivity in this system basically changed everything because now you could create a superconductor out of a very cheap material like graphene simply by introducing this twist between successive layers. Graphene or graphite itself is not superconducting. Okay? And since that discovery, the field itself has exploded. So there's correlated insulator behavior, superconductivity, orbital ferromagnetism, strange metal behavior, Chern insulating states, nematicity, fractional Chern insulators, the fractional quantum anomalous Hall effect, Fermi-fermion behavior, and so on, in various types of systems, twisted like graphene, the example of graphene that I showed you, in different ways. And there's lots of examples here of these different types of systems and this kind of exotic and nice behavior. I'm not going to go through more details. I just wanted to give you sort of a big picture of how many interesting and exciting things are happening in this field, all because of this relative twist of between successive layers. So one more word about this before I tell you a little bit more about our own theoretical work. And this is again from the work of Pablo Jarillo Herrero at MIT. This is again the situation of correlated insulator and superconductivity in twisted bilayer graphene near this special angle that produces these effects. So what you see here is on the horizontal axis is the carrier density. That's the number of electrons in the system relative to the neutral system. 0 is the neutral system. So on this side you add some electrons, on this side you remove some electrons or you create some holes. So on the vertical axis is the conductance, which you can equally well interpret as the density of states, the density of electronic states in the system. So you see this kind of behavior, this kind of humps, where the electronic density of states is. And the horizontal axis can be thought of as equivalent to moving the Fermi level. So you change the place of the Fermi level, so you add electrons to the system on this side or remove electrons on this side, and that's the density of electrons that you observe. That's this diagram. On the bottom here are two different diagrams. The horizontal axis is the same as this one, is the carrier density, the number of added or removed electrons from the system. The vertical axis is temperature. And the color coding here is the behavior of the system. So, and this is for two different angles, 1.16 degrees twist between the two layers of graphene, or 1.05 degrees twist. And as a function of temperature, you see superconducting behavior in this range of temperature and doping. Also superconducting over here. In this range, it's an insulator, a Mott insulator. Over here, it's a metal, and over here, it's also a metal, and so on. And the behavior in this slightly different twist angle is very similar. Why am I going through all this? Because there's a striking resemblance of this phase diagram of the different phases that the system undergoes as a function of doping and temperature to high temperature superconductors. So here's the phase diagram of high temperature superconductors, the cuprates and related systems. So there's a superconducting dome here and here. The horizontal axis again is doping, a number of electrons or holes. The vertical axis is temperature. The yellow regions are labeled AFM. This stands for antiferromagnetism, but it is equivalent to saying that in these yellow regions, the system is an insulator. But there's also more interesting phases here in the high temperature superconductors, a charge density wave phase here, a phase called pseudo-gap, another one called strange metal, and so on. And out here, the green regions are the sort of normal metallic behavior referred to as Fermi liquid. Okay, so we don't know if all these phases also exist here, but the basic structure is there: superconducting domes separated by an insulating region. Here's the insulating region and other metallic kind of behaviors. And this made things very exciting, because if the phase diagram is so similar, then that implies that the physics are very similar. And then you could imagine studying the very exciting and interesting and complicated physics of the high temperature superconductors, which are difficult to make from a chemical point of view and to control all the doping and so on, into a very, very simple system, twisted bilayer graphene near the magic hand. And that's one of the main reasons why the field has exploded so much, because it gave us a practical, simple system on which to study essentially the same physics as what is more or less seen in high temperature superconductors. By the way, high temperature superconductivity was discovered in 1986. So that's 40 years ago. I remember it very vividly. I was a graduate student at that time, and it was a revolution. It was really fantastic. And we still don't have a theory of high temperature superconductivity, at least not at the level that we understand the conventional superconductors through BCS theory and so on. Okay, so this was sort of a quick and broad view of experimental observations and motivation of why these systems are very, very interesting. I'm going to switch gears now and go to the theoretical side and try to make sense of not exactly everything, but at least some aspects of what I'm presenting here. Okay, so let's start with the physics of graphene, a single plane of graphene. I wanted to revisit this because there's some important connections that I'll be making, and I wanted to make sure that everybody is familiar with this. So this is the band structure of graphene as calculated in many places, but here's a nice reference. A bit of a product placement. Essentially, by solving the Schrödinger equation in the first Brillouin zone, the Brillouin zone is outlined here by this black hexagon, you find that the energy of the electronic bands near the Fermi level at 0 is linear in the momentum. And that was a very exciting discovery. And of course, when you plot the energy as a function of the two components of the momentum, kx and ky, it forms these so-called Dirac cones, linear behavior near these points, near the corners of the Brillouin zone, the k points. This was very unusual and produced a lot of excitement in the physics community. Interestingly enough, the density of states at the Fermi level is exactly zero. There's no electronic states available at the Fermi level. But if you move a little bit away from the Fermi level, either positive or negative, you find states that you can occupy there. Or the region where you see very important, interesting behavior is when the density of states tends to have these kinds of divergences. So the density of states nearly diverges here. Those are called Van Hove singularities. And it was realized that if you could access these regions here, either on the hole side or on the electron side, you could have very exciting physics because nature doesn't like divergences. The system would respond by doing some interesting kind of behavior, and you would get all sorts of interesting correlated electron behaviors. So that had been hypothesized. The problem is that it's impossible to access these regions of diverging density of states, because if you look at this range of values here, this is in electron volts. These correspond to 2 or 3 electron volts away from the Fermi level. And it's very, very difficult, close to impossible, to access states that are several electron volts away from the Fermi level. And that's very important for what's coming next. Okay, so what about what happens in the case of twisted bilayer graphene? Well, this is a brilliant, simple model, the so-called continuum model by Alan MacDonald and collaborators. Actually, this was published in 2011, several years before superconductivity was observed in twisted bilayer graphene, even before people were able to create these twisted bilayer systems in the lab. So this was really a theoretical prediction in very beautiful way. So here's what happens. So I mentioned that there's a hexagonal Brillouin zone in one graphene layer. Well, you have 2 graphene layers, you have 2 hexagonal Brillouin zones. The blue one is from the top layer and the red one is from the bottom layer. And at each corner of these Brillouin zones of each individual graphene layer, you would have a set of Dirac cones, just like I showed you a moment ago for an individual graphene layer. But because of the Moiré periodicity, the Moiré superlattice, you would have now a supercell Brillouin zone in reciprocal space, which is this one outlined by black. So that is the Brillouin zone of the Moiré scale. And if you put those pictures together, you realize that in each supercell Brillouin zone, in each one of these black hexagons from the Moiré pattern, you would have a Dirac cone from the red layer and a Dirac cone from the blue layer. So you have 2 sets of Dirac cones in each corner of the supercell Moiré Brillouin zone. So this is called valley degeneracy, a blue and a red Dirac cone at each corner, and those are labeled as K and K prime bands relative to the original graphene layer. So, so this is for 2 individual layers that are on top of each other with a relative twist, but not talking to each other, unrelated, okay, not still interacting and communicating. If you allow communication and interaction, this is how the picture changes. So basically, the Dirac cones, the blue and red Dirac cones intersect at some point, and the interaction lifts this degeneracy and creates these new bands. And you can tell from this very simple picture the distance between the points of the Dirac cones scales as 1 over the Moiré length. The Moiré length, of course, is inverse to the twist angle. So this is basically proportional, this distance proportional to the twist angle. So the smaller and smaller the twist angle, the closer and closer the Dirac cones come together. And by this layer interaction and pushing these flat bands together, you get flat bands. And this was a key point in realization, because the flat bands create their own density of states. Here's again a diagram of the energy on the vertical axis and the density of states on the horizontal, and the flat bands create these density of states. And compared to graphene density of states, you would have to multiply the graphene density of states by a factor of 1,000 to make it visible on the same scale. In other words, you have enhanced the density of states due to the presence of the flat bands by roughly a factor of 1,000. Moreover, this range now where this enhancement happens is a tiny, tiny energy range because the bands are so flat. In fact, the bands, as you'll see in several examples in the few moments, have dispersion of the order of few milli-electron volts. And this is certainly very easily accessible experimentally. So that was the huge discovery, the huge realization. So the simple model that Bistreizer and MacDonald put together involves a Hamiltonian like this. So along the diagonal of the Hamiltonian are the individual graphene layers, graphene layer 1, graphene layer 2, each one of them linear in momentum, as we explained, and the other term, the off diagonal, is the interaction. You put all this together and you produce this kind of bands from the combined system, and for very special angles, so-called magic angle, you have these very, very flat bands. So these are from more realistic calculations based on the continuum model. They're still not quite realistic enough because they miss certain important features. For example, there is no band gap between the flat bands and the rest of the bands. And this is something that I emphasize here because the presence of band gaps separating the flat bands from the rest is a crucial feature of the system. And without this, you wouldn't be able to find any of the complicated phenomena that I was alluding to, and I'll describe in more detail shortly. Okay? Now, flat bands are great for the reasons I described, but they're very problematic from a very different perspective. And let me try to address this now. So this is a slightly oversimplified picture, but the presence of flat bands produces a puzzle for superconductivity in twisted bilayer graphene. Very roughly speaking, hand-waving sort of argument, the critical temperature for superconductivity scales like the value of this tensor. There's a tensor which is written more explicitly here, called the superfluid weight tensor. So in order to create the superconducting state, which is the superfluid in a certain sense, you have, this is the relationship between the critical temperature and this tensor. And this tensor basically tells you, has two contributions. One, the conventional contribution, which comes from the curvature of the bands. So, this component of the tensor is proportional to the second derivative of the bands. But if you have completely flat bands, there's no curvature. So this component of the tensor vanishes. So all you have is this other component of the tensor, which is called the geometric component, and is proportional to this tensor. So this is all geometry if there's no dispersion. And what does that mean exactly? So here's what the quantum geometric tensor looks like. So this is this capital Q, and it has two components, the little g, which is the real part, and the capital omega, which is the imaginary part. The imaginary part is the very curvature, and the real part is the so-called quantum metric, which enters in this expression. And this has to do now with the geometric properties of the bands in the following sense. So this expression involves partial derivatives of the bands. U sub k is the wave function of the bands, which are, of course, functions of the wave vector. So this includes two partial derivatives. That's where the tensor components come from, with respect to ki and kj, of the bands with respect to momentum. In other words, the nature of the electronic states, uk, changes as a function of k as you go through k values in the reciprocal space. And this change cannot be trivial, because if it's trivial, it doesn't give any contribution here. It has to be a non-trivial change as you change the momentum index of the electronic states in the system. That's the essence in this, as best as I can describe it in words, not with fancy formulas. And I'll come back and try to illustrate this in our case. And where does this come from? We like to have an atomistic picture of how things happen in materials, because that gives us the possibility of making predictions and giving detailed explanations for experimental observations. So an atomistic theory should be able to address these types of questions. What exactly is the atomic structure in twisted bilayer graphene and other related systems? How does it affect the electronic states? And where does the correlated electron, the Mott insulator behavior originate from? And what is the nature of the superconducting state? We have fully addressed the first two questions, and I'll try to convince you about that. We're making some inroads about trying to understand this a little bit better, but of course we're certainly far away from having a picture of where the superconductivity comes from. There's a lot of work along these lines and a lot of exciting ideas, and we hope to contribute to these ideas by guiding many-body theories on the right type of physics that is going on in the system. Okay, so for an atomic structure of a solid, any given solid, we have a very well-developed theory, and this is, of course, density functional theory due to Hohenberg, Kohn, and Sham. It was developed in the mid-1960s, so that's 60 years ago. Walter Kohn got the Nobel Prize for his contributions to this, and basically we solve Schrödinger's equations for individual electronic states in an external potential, which includes the presence of the ions, and in an effective way, the presence of all the other electrons through Coulomb interactions and through exchange and correlation effects, taking into account in a mean field theory. So it does have its limitations. So first of all, the fact that we can write these equations is due to the assumption that we're dealing with fictitious independent particles. So the many-body wave function is basically written as a product of these fictitious independent particles. So in this sense, this theory cannot even start to address many-body physics. We have to go to a very different type of theory to discuss many-body physics. So keep that in mind. But it does, with an approximate exchange correlation potential, which is well established from other studies. I don't have time to explain this. We can make predictions and explain and guide experiment. It has its own limitations. It can only handle of order 100, at most of order 1,000 atoms or so, and it is based on crystal structure. So there's a periodic arrangement of the atoms in the solid that is implied here. So how do we use some of this, at least, in order to address the questions that I mentioned? And first, let's worry about what is the atomic relaxation? Where are the atoms? If you look at the pattern of superimposing a blue layer on top of a red layer, two layers of graphene, without any relaxation, you see regions where the two lattices match almost perfectly. Those are called AA regions and correspond to high energy stacking of the atoms. You see other regions where the top layer and the bottom layer are basically perfectly moved relative to each other, so that the top layer hides only half of the atoms of the bottom layer. So you see here all the blue atoms, but only half of the red atoms. And this is called AB or BA regions. Those are equivalent by symmetry. And the rest is kind of a mess. You cannot see a very clear pattern in the rest of the structure. This is for 3-degree twist. If you do a twist at a smaller angle, these regions in the unrelaxed ideal layer simply become larger. They just become slightly larger. What does that picture have to do with what experiment shows? Well, in order to do that, we have to have a way of finding the optimal structure of the system given the atomic positions, or rather move the atoms so as to attain the lowest energy structure. Well, in these types of situations, the atomic structure involves thousands of atoms, so it's very hard to do calculations from the DFT perspective. And working together with the group of Mitch Luskin, and he's a mathematician at the University of Minnesota, and his collaborators, we came up with this new way of looking at the system. So basically, you look at all the local environments. We refer to this as configuration space approach. So in this region, you have this local environment between blue and red atoms. In this region, a slightly different set of local environments. In this region, different set of local environments. And you can generate in real space all these possible local environments by simply taking one layer and displacing it with respect to the other layer. And by doing so, you reproduce all the local configurations, at least for small enough angles. This allows us to change integrations over momentum space, which is the traditional way, the standard way of doing these kinds of calculations in condensed matter physics, to integrals over configuration space. Capital omega is all the set of possible local configurations, and little omega labels those configurations. So this is basically what we have done, but this implies that we have a Hamiltonian, we need a Hamiltonian of finite range, because that's all it takes to describe all these local environments. With this type of Hamiltonian, which I'll mention in a second how we get it, basically we can minimize the energy as a functional of all the atomic positions. So there's two contributions, one from interlayer interactions and one from intralayer interactions. This comes from elastic linear elasticity theory, which is good enough to capture all the energy changes due to change in position of atoms within the layer. And the interlayer is an integral over an energy landscape for all the displacements, relative displacements of the two layers, which generate all these local environments that I mentioned, and include here a functional U of changes in the rigid displacements. So minimizing this with respect to this functional gives us the lowest energy. And with this, we can produce these kinds of pictures. So here is a color-coded version of the energy landscape that I mentioned. Namely, you take one layer and you translate it with respect to the other layer, a single atomic unit cell, and you produce the energy landscape. Black is low energy, red is high energy, white is intermediate. The energy landscape, you can calculate gradients, which essentially can be translated into the forces, the displacements of the atoms. And with this, you can produce this picture, which includes now the full atomic relaxation that gives you the lowest energy configuration. And here, you can easily see these triangular regions, which correspond essentially to what is seen experimentally. Yes?
How do you, so because the Moray twist is, it's not the global minimum, right?
Correct.
So how do you go to a local minimum but prevent your code from going to the global AV stack minimum?
Yeah, first of all, we don't do this, the relaxation, the energy landscape is for a single atomic unit cell. I went too fast on that. You don't need the full Moray, you just need the 2 atom unit cell of graphene in each layer, okay? And so we never minimize the I'll show you later actual calculations with the full unit cell with 13,000 atoms. Sure. And the way that you don't go back is because you have a relative twist to begin with. So the whole lattice cannot untwist because that would cost a huge amount of energy. Okay. I don't know if that makes sense.
Yeah.
Okay, good. Okay, so this is the pattern that you see experimentally, triangles, up and down triangles. Here are the up and down triangles that we're talking about. And here's the picture that you should keep in mind. So the pattern that you see here in experiment and in theory consists of these large triangular regions. Those are the so-called AB or BA regions, which are equivalent by symmetry. They're separated by these thin lines, the domain walls. You see these thin lines here in the theory. You don't see them in experiment because they're just too narrow on this scale. This scale is hundreds of nanometers. Maybe this is the microns. And these narrow, very narrow circular, hexagonal, or almost circular regions, here you see them in the theory. In experiment, again, you don't see them. They're tiny. And these are the so-called AA regions, which are the high energy regions. And these are the low energy regions. So basically, the system tries to create as large triangles as possible because they correspond to the optimal stacking of the layers. But because of the overall imposed twist, relative twist, you cannot avoid having domain walls between these triangles and these corner regions, which are the so-called AA and AB. Moreover, if something really magnificent happens from a geometric point of view, these AA regions, the small regions that are energetically unfavorable, have an extra twist. They're not twisted as much as the global twist. They're twisted by an extra amount, and that amount is fixed. The green regions untwist, twist slightly in the opposite direction from the global twist, and that allows them to be very close to the optimal stacking. And of course, there's the domain walls in between.
Sorry, in the experimental picture, what's basically the grayness scale means? Why some are less?
Good question. Yes, because in experiment you can't have a perfect bilayer graphene as we do in theory, because there's always some amount of residual strain, and the residual strain sort of distorts the pattern in the middle.
And the density of this blackness, what does it mean physically?
Okay. The reason why one is white and the other is black is because this is scanning transmission electron microscopy, so it's done not exactly perpendicular, but it's slightly off. So one of them looks a little bit brighter, and electrons can go through easier, and the other darker because of the slight off. And that's how you see the two different.
But from the theory point of view, they should have exactly the same.
They're equivalent, yes, exactly. But because the slight deviation from being normal breaks that symmetry, you see slightly different. Okay, fantastic. Okay, but keep this picture in mind because we're going to come back to it. Okay, now, these are pretty pictures that I showed you. We've done much more detailed work to establish that what we see in theory really corresponds to what experiment sees. And this slide captures this. I don't want to go through the details. Basically, all these dots from scattering experiments, diffraction spots, contain a lot of information about the local structure. And when you analyze the shape of these dots or the sub spots in each one of them, you recover this information and you can compare it to theory, and theory and experiment are in very good agreement. So it's not just pretty pictures that I showed you. We really have quantitative agreement. Okay, now let's go back to the local Hamiltonian for the electronic states. Again, I'm going to run through this very fast because it's a little bit technical and you don't need the details. Basically, what this slide tells you is I can take the block states, which are eigenstates of the momentum, and with a linear transformation, transform them into localized states, those which are centered around some position in space R. Those are called Vanier states. So this is a simple unitary transformation, and I can impose constraints on that unitary matrix to do the optimal change of basis. So it's essentially a change of basis, and that gives us a local basis which produces the same bands as the extended block states. So this is what the local basis looks like, and it consists of a pz orbital. So this is at the atomic level now, at the atomic scale, and higher orbital momentum contributions. And when you take these kinds of localized states at each atomic position, and you include their interaction, as we can compute it from theory, you produce this kind of diagram, which is now the density of states on the vertical axis as a function of twist angle on this axis and the energy on this axis. At no twist, you have two layers, and there's a minimum here in the density of states. So this is the position of the Fermi energy. As we talked, graphene is a semi-metal, zero density of states at the Fermi level. But if you go to around 1 degree of twist or so, the density of states shoots up, huge density of states here for this twist, and you see the effects that McDonald's very simple model was also predicting. So this is from our calculations which involved all the way up to, I think, about 50,000 atoms at that time, with this simple model, tight binding Hamiltonian, derived from the ab initio calculations that I was mentioning earlier, based on the configuration space approach. So this is when we came up with the word Twistronics. So we introduced that in the literature, and we're kind of proud about this because it really caught up, as you mentioned, and now it represents the whole field. So, putting the two things together, this is the atomic relaxation that I already told you about, seen here from a slightly different perspective. The dark regions are the triangles that I was mentioning, which are close to each other in distance, exactly the same as in graphite. The red regions are the AA regions, where the atoms basically repel each other because that stacking is energetically unfavorable, and of course there are the domain walls between. And the repulsion is quite strong. This change is about 10% in the distance, in the original distance between layers. And it has a big effect in the electronic structure. So this is the electronic structure with the full relaxation, and this is without relaxation, because since we're doing theory, you can just freeze the atoms in the unrelaxed positions and do the corresponding calculation. So the big difference is the presence of these gaps. So this exists in theory, but it also exists in experiment. There's no gaps without relaxation, and I also mentioned that in the simple continuum model, or a la this type of McDonald, there's no gap. The reason for this importance is that it separates the flat bands from the rest of the states. And this separation actually gives us some level of understanding, the detailed understanding of what the geometric effects in the system come from. So the theory that I just told you about basically gives us density of states as a function of the energy. These are the single particle bands that we calculate, the flat bands, separated by gaps from the rest. And this is the corresponding experimental picture. Red and blue shaded regions are zero conductance ranges where there's no states. So these correspond to band gaps. But still, this is a long way. This theory is a long way from what is actually seen in experiment, because in experiment you have all this extra structure in the density of states. So basically we would like to be able to produce something like this. Go from the single particle bands that come from the DFT type of calculation to something that involves sub-bands. I labeled them 1 and 2. These are basically sub-bands on the hole side and on the electron side to capture what is going on in the experiment. But as I already mentioned, you can't do that at the level of density functional theory. You have to invoke a very different type of picture. And this is what is referred to as Hubbard physics. So you have a situation where you have electrons hopping between different lattice sites. That's the kinetic energy term captured by this part here. But you also have electrons on the same side, labeled by I, with up or down spins, and there's a big energy cost when you do that because of the Coulomb interaction, the Coulomb repulsion between the electrons on the same side. So two electrons on the same side have to pay a high price in energy, and electrons, when they are allowed to move around, they gain kinetic energy. That's this contribution. Now, this simple model, if you are close to half filling, that is one electron per site, produces a state that is insulating, and produces this kind of half-filled band with a gap separating the two half-filled bands. Now, in the last year or so, by some technical improvements and advances, we have been able to do band structure calculations for twist angles all the way down to about 1 degree, a little bit below 1 degree, corresponding to 13,500 atoms, including full atomic relaxation, band structures, and all the information about wave functions in the flat bands and the neighboring states separated by the band gaps that are dispersive bands, have much higher dispersion than the flat band. So these are the group members who are responsible for this, and I'll show you some pictures describing all this. First of all, the atomic relaxation. We went through that. It's exactly the same. So this is now atomic relaxation without any tricks about configuration space, generalized energy, stacking fold energy, landscapes, and so on. This is straightforward minimization of the energy in large unit cells. The calculations agree exactly with the earlier predictions that I already mentioned. And I'll focus now on some features of the electronic states themselves, which are shown here schematically, so that you can be oriented about what the pictures mean. So this is a picture of the Moiré cell, the blue outline here, at a 5-degree twist. That's a relatively large angle twist, and the reason I'm showing you this is because at this relatively large twist, the Moiré cell is relatively small, so you can see the atomic positions. Those are the little blue dots here. So here are the blue dots, which are the atomic positions. That's the Moiré cell. And the little speckles here are the weight, absolute value square of the wave function. Because it's hard to see all this detail, we do a convolution of the wave function with a Gaussian. So you see sort of the average of the wave function magnitude spread over all of the Moiré cell. So that's what this wave function convoluted with a Gaussian will look like on the Moiré scale. So now I'm going to go to much smaller angles, all the way to 0.99 degrees, 0.987 degrees, which has much, much larger Moiré cells and many, many more atoms per unit cell. So you can't see all these details, but you can still see the interesting features of the wave. So here's now 1.08 degrees. By the way, this choice of the twist angle was made because it's very close to the experimentally observed magic angle, where the flat bands and superconductivity happens and so on. So this contains of order 10,000 atoms in the US, 10 or 12,000 atoms, something like that. So this is the energy scale, of course, the Moiré Brillouin zone, high symmetry points in the Brillouin zone. Those are the flat bands, separated by gaps from the rest of the bands, and these are the wave functions. So let's look at the blue wave function. So this is the character of the wave function at this point, and this is the character of the wave function at these points. And let's look at the red wave functions, the ones outlined in red, circles here or squares here. So this is the red wave function here, these two panels. This is the red wave function here. You can see this is the same wave function, and this is essentially the same wave function. But this wave function lives in two very different bands, and so does this one. So it's this crossing of the wave functions that produces the geometric effects. Now, if you calculate the derivatives of these states with respect to k, you will find a non-trivial contribution to the geometric tensor that I was describing. So that's where this comes from. And it's very clear from these calculations. Moreover, we see something even more exciting. So this now is a different set of states that I'll show you. So I will show you states for what happens when you compress the two layers together. They're twisted, but you do an additional compression of the two layers. It is known experimentally, and actually we had shown that from the theoretical point of view, that compressing the two layers is equivalent to shifting the magic angle, the angle where the bands become very flat, to smaller values of the twist. In fact, that was a prediction that we had made that was later verified experimentally by the group of Corey Dean at Columbia. So here's what happens when you compress the two layers. Delta Z equals 0 means no compression at the original separation Z between the layers. These are the bands, and the flat bands only. I'm not showing you the rest. And notice that I'm showing you a very expanded range here. So this is 10 milli electron volts. This is 20 milli electron volts. So these are very flat bands indeed. And as you compress the layers, they become even flatter and flatter. And the two dots that I have shown you here in cyan and purple, again, as you increase the compression, switch positions again. So, and here are the wave functions to explain this. So here's the cyan wave function corresponding to this point, and it is the same here, and all of a sudden it's down here. So this is the same wave function, as you can easily tell visually inspecting this. And this is the same wave function, the purple one, which used to be here, and after compression it ends up here. So again, there's another switch in the character. Not only the bands have crossed along the K values, as I was showing you earlier, but now you have mixed what used to be electronic states above the Fermi level to Hall states below the Fermi level. So there's an additional type of transition, topological, geometric type of transition that we are predicting. And there are hints in experiment that this is indeed the case, because typically superconductivity is more pronounced for holes in these systems, but after a certain twist, they become superconductivity becomes more pronounced for electronic states. So, which is equivalent to switching the character of electrons and holes in the system. So this is very exciting, and it's another example of what we are able to do. So very quickly, I want to sketch out what we are trying to do at the moment. So let me just emphasize the importance of the lattice here. So this is a square lattice. It's bipartite, and if you put equal number of electrons of upspin and downspin here, you can make a very nice underferromagnetic arrangement. This is the kind of situation that corresponds to the underferromagnetic ordering, the insulator phase in high temperature superconductors, which all rely on a square lattice. Now, in what I was showing you, there are other types of lattices that enter, like the honeycomb lattice, which is bipartite, and you can again arrange up and down spins of electrons in this to make an underferromagnetic state. In a triangular lattice, things are more confusing because you can't have these kind of underferromagnetic order, so more elaborate type of spin arrangements are needed to produce an ordered phase. And when you try now to do this kind of theoretical modeling of many-body physics in the language of Hubbard model that I was mentioning earlier, so here's the Hubbard model that I told you a moment ago with the T and U terms. This is equivalent to the so-called TJ model in the limit of large U. So the ratio of T over U is very small. This model is equivalent to this, which consists again of a hopping term and a spin interaction term. And it's this spin interaction Heisenberg type spin interaction term that produces the underferromagnetic ordering here or here. So that's all well and nice if you have a bipartite lattice, as in the case of a square lattice or a honeycomb lattice. Moreover, it gives you a nice way to sort of motivate the reason for electron or hole or hole binding to produce a superconducting state. For example, if you have two holes in this underferromagnetic system that are far apart, you break so many underferromagnetic bonds around this one and so many around this one, 4 here and 4 here. If you bring the holes closer together, you only break a total of 7 underferromagnetic bonds. So that's an energetic incentive for the holes to bind. And it's believed that that kind of mechanism is related to the superconductivity seen in high temperature superconductors. So that's the high temperature superconductors. Those are the lattice, the crystal structures. A common feature is this two-dimensional plane of copper and oxygen atoms. And this is what I was just showing you a moment ago. And it's only one electronic state that is relevant in this. And again, you can find that in nice papers going back several decades, or as a problem in this book. And there's only one electronic state here. Okay. single particle state. And you can break that along the lines that I was mentioning earlier into sub-bands with half electrons spin ups and the other half spin down and so on. In the lattice that we're dealing with it, in twisted bilayer graphene, it's a disaster because we have this complicated pattern that I explained earlier coming from the relaxation pattern. And if you analyze this relaxation pattern that I showed you, it consists of three different lattices. These little sites here, the AA sites, form a triangular lattice. That's the triangular lattice. The domain walls form a Kagome lattice, and the ABBA triangles form a hexagonal lattice or a honeycomb lattice. So all three lattices together, and that's a mess. And not only is it complicated from the geometric point of view, but you need lots of states to do this. So this is what this diagram is trying to allude to. You need all these three lattices that I was telling you about. You can analyze them in different types of orbitals. The blue and orange are the triangular lattice. The green one is the honeycomb lattice. The purple is the Kagome lattice. And it's a real puzzle now how to go from this to this symbol. So very, very recently, we have been able to break the system down to a few bands. So here are the flat bands. Here are a few bands below and a few bands above, and throw away all the rest. So just keep that as the essential features of the model. This is the kind of wave functions that correspond, localized Wannier functions on the Moiré scale now that correspond to some of these bands. And with this information, we can do this kind of calculation, for example. So you need these 10 different localized orbitals on the Moiré scale, produced by the same methodology now, but for a much larger lattice. And with these localized orbitals, you can calculate these quantities, like the on-site interaction, on-site repulsion of electrons, effective electrons on these orbitals, as well as the hopping matrix elements that I was telling you, which are the ingredients of the more complicated Hubbard-type model that I was trying to hand-wavingly describe. So that's where we are. This is fresh off the computer, basically. We just got this very, very recently, and I think one of my students will be presenting it next week at the March meeting, very fresh results. Here are the people involved in these types of calculations that I was mentioning already. I showed already several pictures of them. And we've done many, many other types of studies, theoretical studies of two-dimensional systems. I just focused on the twisted bilayer graphene, the very first item here. But it is a very exciting, rich, and wonderful field to work on. Thank you very much for your attention. I'll be happy to answer.
All right, I think, yeah, right, go ahead.
Thank you very much, very interesting. So the connection between the phase diagram of the twisted graphene and the FTC cuprates. Cuprates have multi-layers too in the atomic structure, but they're not twisted or shifted. So how this parallel appears in your opinion?
Okay, so these are the cuprates. Okay, so this is the copper-oxygen plane here. Lots of other ions here, lanthanum, strontium, oxygen, and so on. It is this plane that dominates the physics. Everything that has to do with superconductivity is related to these planes. And it's an oxygen, 2 oxygen atoms per unit cell, and a copper atom that combine their orbitals to produce this single electronic band, which then can be used in Hubbard-type models. So that's the only connection. I just wanted to make that connection. So
the fact that there are multiple layers is completely irrelevant.
Yes,
right? So
basically, yes.
Physics goes around.
Correct. Those layers are so far from each other, essentially, that they don't really communicate. There's many of them, okay? But they're not really coupled strongly. All that physics is. So in a sense, it's great because it's also a two-dimensional system, essentially. But these are much more complicated. Chemically, it's a nightmare to actually make them in a controlled fashion to have the right number of holes or electrons and so on. That's why. And this is much, much simpler than this. So our problem in terms of the actual lattice that we have to deal with is really a very challenging problem, I would say.
And maybe one quick technical question. So when you talk about these DFT calculations, you said that locally the twist is equivalent to a shift.
Correct.
But this the shift corresponds to more a distance of infinity, right? Because you never repeat the pattern.
Correct.
So how do you do the shift for multi-body calculations then?
Well, okay, so we take advantage of the closeness between the shift and the twist in terms of determining the local atomic arrangement.
Okay.
So for different amounts of twist, we generate different local arrangements here. And then we collect all these and say how many of these we need to describe the full system. And then we do this integral over the local arrangement.
Okay, so it doesn't mean that if you just shift the graphene layers, you do the same physics. It's just
Correct, unrelated. It's just a trick to get all the local arrangements, the local configurations that we need to do this integral. But we do this calculation now at the 2-atom unit cell, which is much easier.
You saw?
Sure. Just a quick question. From an intuitive perspective, the reason that you have the gap opened in the flat band region after considering the relaxation, was that because you concentrate the, you actually squeeze the A side?
Yes.
And the interaction there is actually becoming larger, so that the tunneling is becoming more dramatic.
Correct.
Okay.
Yes.
So another
Yes.
quick question is that, do you think the observation, for example, in transport experiments, people could observe topological properties in the twisted graphene system? Do you think the relaxation is actually a necessary ingredient to explain? Because what you have shown later is that these kind of different honeycomb,
Yes.
kagome, or all these kind of geometries, they are very much topological
Yes.
related. So these actually indicate that relaxation is a necessary ingredient to observe the topological features in.
Absolutely. Yes.
Okay.
Yeah. Absolutely.
Yeah. So the last thing is that can you clarify a little bit for the geometry effect? The geometry you are talking about, the quantum geometry you are talking about, is not only just the integration of Barry curvature in quantum space. So actually, in addition to that, there's something else.
It is basically something like the Barry curvature. So in this tensor, in the so-called superfluid wave, it's this pair thing, which is the real part of the quantum geometric tensor, and the imaginary part is the Barry curvature. So it's something similar to the Barry curvature, just other components of this quantum geometric tensor. But it's all related to these partial derivatives. So this little g is the real part of capital Q, and the Barry curvature is the imaginary. So they're closely related. Same physics in a sense. And you know, the integral of the Barry curvature is a certain number and so on. So they're all related.
I guess related question to, so your famous lattice that you get with,
Yes.
triangles, right, when you parse.
Right.
And then somewhere I saw something that looked almost like a kagome.
So
So, you know, in I guess insulating systems, should I say, or magnetic, you know, that frustration. So if you take that parallel, what is frustrated here? Is the Barry curvature? Is this geometry tensor
yes.
that's frustrated? That, you know,
Yes.
then makes your calculations kind of, you know, intractable.
Yeah. Was frustrated. Okay, this is a very good point actually. Here, so if I look at these bands, okay, those are the flat bands, and there is no way to produce this kind of dispersion in a triangular lattice. If you look at the basic lattice of the
Hexagonal, whatever.
oh no, it's triangular.
Triangle, yeah.
Yeah, it's triangular, exactly. If you look at what the experiment
Yeah.
sees, it really looks triangular. This is a triangular lattice. Forget the triangles, you know, just the repeat.
Yeah.
That's a triangular lattice. Okay. But there's no way to produce this band structure that I was showing you from a triangular lattice. So, and this was realized very early on. There's several very nice, beautiful theoretical papers written about this one from my colleague at Harvard, Ashwin Vishwanath, and they called this obstruction and fragile topology. Basically, they were trying to say with these words that if you go from this region, from gamma, to a different region, in case you find very different character, and you get this crossing. So that's what obstruction and fragile topology meant to capture. So this is what we're seeing here directly from ab initio calculations. In other words, the frustration comes from the fact that if you look at these spots. These are spots in a triangular lattice, but there's no way to produce this kind of band dispersion in a triangular lattice. So there's definitely more to it than that. You can't just stick with a triangular lattice and say, I'm done, this is all I need. That's completely wrong. And that's why I was trying also to bring in the importance of the relaxation, which clearly tells you that, it's not a triangular lattice, you have this, so if you look at this, the red, the orange hexagons make a triangular lattice. But the green triangles make a honeycomb lattice, and the domain walls make a Kagome lattice. And you can't forget them, because the states have weight in all these three regions, and they're coupled.
So you have a huge degeneracy, basically, what you're saying, which frustration.
That's, so, and the triangular lattice is certainly frustrated in terms of having an antiferromagnetic order. You can't have it there. You can have antiferromagnetic order in the honeycomb lattice. But that's like looking at the green triangles only and forgetting the rest. Well, you can't.
In the interest of time, maybe one last question. Aaron?
So if you want to take this lattice and you want to say, put on Hubbard or whatever, look for the superconductor, where does the superconducting phase actually sit because it's so modulated? Should I think of this? Are you thinking of this as some version of like an FFLO state where you have some spatial modulation of the superconductor? Does it like sit only in the domain wall?
Yes.
Where is it?
Yeah, that's I don't have a good answer for your excellent question, but I think that's the essence of the problem. How can you pare down this model to its absolute essential features to capture this? I think you definitely have a triangular lattice, which is perfect, but you also have intermixed with that at least the Kagome lattice, and that's why you can afford to have ordered states, even though the triangular lattice does not allow you to do that. That's why you can have antiferromagnetic ordering or something equivalent, because you don't hop directly from triangular site to another triangular site. You hop through it, through the domain wall, through the Kagome lattice. And it's the coupling of those two that would produce something interesting. Now, we're working actually toward that goal to have a model with the absolute minimum amount of information from ab initio that can capture these things, but we don't have a full answer yet. So there are other efforts in the literature to do that. I didn't have a chance to show you, just to flash one more thing. So there's any other very interesting ideas out there. Here it is. Yes. So early work tried to capture this kind of frustration that we were talking about, but they ended up with very delocalized orbitals. And so here's work from Vishwanath and co-workers. This one's kind of more recent work by the group of Bernevik at Princeton basically has these two flat bands and these two other dispersive bands and calls these the heavy fermion bands. So it's this coupled. So for us, the flat bands are on a triangular lattice mostly, and the other bands, the dispersive bands, are on the Kagome lattice, and those are coupled. So that's the kind of picture that we are trying to build to capture these effects. And other theories do some similar types of tricks. But at least we have all the information from ab initio. There's no adjustable parameters there. We know what the on-site interactions are. We know what the hopping matrix elements are. It is the minimal information that we need to build a sensible model to be answered soon, hopefully.
All right, on that note, let's thank Efthimios. Yeah, really.